In the world of manufacturing, we use the terms tolerance, accuracy, and precision to describe three separate but closely related concepts involved in making and measuring a finished part. In today's episode of Engineering 101, we want to briefly discuss the differences between these terms. Stay to the end and we'll share a little secret that can save you a lot of time and money on your next project. Also ask a bonus question about measurement that we'll answer in our next video, so stick around for that. First up, let's talk about accuracy. We define it as how closely a result comes to being equal to the ideal or the standard. For example, if we want to make something that's exactly 1 meter long, the first thing to do is to machine it very well. Then, we measure the object as carefully as we can against a known and recognized standard. In this case, that's the ISO International Meter, which, like all the other ISO standards, is a fixed and immutable physical constant. The closer that our part can be measured against the dimensions of the standard meter, the more accurate we say the object is. The word precision is often used interchangeably with accuracy, but in fact precision refers to repeatability. In our example with the meter, we can make one object that's very accurate, but that doesn't tell us much about how good our manufacturing methods are. Maybe we just got lucky that one time. However, if we make an accurate part consistently over a period of time in many parts, then we've achieved precision. Where does the term tolerance fit in? Tolerance describes the degree to which a measured value deviates from the ideal, usually expressed as a plus or minus variance. In our physical world, all objects, man-made or natural, have some degree of variation from one thing to another, even if they appear to be exactly the same. It's inevitable and it's okay. Some amount of tolerance is necessary if you want a mechanical device to be able to move. If it's too perfect, then it would be inert. There's one last concept we want to add before we explain how all this fits together, and that's the idea of tolerance stacking. For example, if you have a complex assembly with many parts, and all the parts need to fit together to perform a certain function, remember that each part will have a tolerance or deviation from the nominal. The more parts you have, the more tolerances can add up, little by little, stacking up. So there's the possibility the cumulative result of all these minor variations can be far off from the nominal. That's why it's essential to not only measure individual components, but also complete systems. Now that we agree on our terms, how do they apply to your product development goals? Well, many designers erroneously believe that very tight tolerances and very high accuracy are always synonymous with good or high quality. And because everyone naturally wants a good product, designers therefore automatically specify tight tolerances in their design drawings, even for features that don't require it, in the belief this will yield the magical and mysterious characteristic we call quality. But here's the secret we mentioned before. Tolerances that are too tight are much more difficult to make, take a lot more time, cost a lot more money, result in higher scrap rates, create problems in other areas of design, and don't necessarily yield a higher quality finished product. If you want to have a happy and stress-free life and get great parts fast with less expense and worry, then please heed this simple advice. Avoid making your dimensions tighter than they need to be for the intended function of your product. Modern machine tools are more than precise enough to make excellent finished parts with standard tolerances. This is one of the best ways to save time, money, and grief when developing your next project. And remember what we said about tolerance stacking? If you're building an assembly with many pieces, don't obsess over the accuracy of each individual component. If your assembly works as intended and has a high degree of reliability, then consider it mission accomplished. Now, for the bonus trivia question. What was the last standard ISO measurement value that was based on a physical object and not a universal constant? Be sure to post your comments below and tune in next time for the answer. And if you want to learn more, please check out Serious Engineering, our ongoing video series where we explore engineering and manufacturing processes in greater detail. We'll leave a link here. Don't forget to subscribe and press the bell icon, and we'll see you next time.